Years later, I would be here introducing the person whose office I was in, okay, who told me the following thing. He goes, Stefan, there are a finite amount of problems in physics. He was referring to my when I was preparing for the qualifier. I said, really? That changed my whole paradigm. Only finite amount of problems? Remember you said that?
Yeah.
But what you didn't tell me is that there are infinite amount of problems in research. Okay. And now I'm learning that, which means I give projects to students. So Jim Valles, who is one of our faculty here and formerly the chairperson for the last 2 terms, and the person that was part of hiring me, bringing me back. Thank you, Jim. No, I have no one need to. So Jim is an interesting, I think, a very inspirational physicist because, after doing his undergraduate at Dartmouth, which is a very, we're always in competition with Dartmouth in terms of being the #1 teaching university. Okay. So hence your appreciation for great pedagogy. Jim went off to UMass Amherst to work with some famous guy in condensed matter experiment, and then went off to Bell Labs, where he transitioned from superfluidity to superconductivity, and of course, Leon Cooper being here at the time, I'm sure it was part of you coming here. But I think the most interesting thing for me personally about Jim, which actually has impacted the way I am as a researcher, was that I remember when Jim first came as a young faculty. I mean, you still look young, you haven't aged a bit. Is that Jim started working on levitating frog eggs with some people at NASA and some colleagues in the biology department. And he was one of the first, if not the first, physicists I knew that was explicitly taking a risk doing biological physics research, a kind of a pioneer. And I just found, I didn't know that actually, that the enabler was another person, another faculty named Humphrey Maris, which is interesting for me personally. I'm going to shut up in a second, because Humphrey, now it makes complete sense, Humphrey, because that's another story, but I went to Humphrey with a crazy idea once, and Humphrey said, really? Go do an experiment on it. I don't know if you remember this. And then I ran off and I became a theorist. Okay. So anyway, it's a great pleasure to have our own Jim Valles. Oh, this is for you. Oh, I'll take this. Great, this is for you.
Thank you, Stefan.
Oh.
Don't choke the mic. Unless things are good. Yeah. It's great to be here, and thank you very much for the invitation, Stefan, on Thursday night. I'm a tad nervous. Maybe the students need to know that. These things are nerve-wracking doing this, and I'm trying something new. I'm going to be talking about something, many things I've talked about before, but there's a kind of a new twist to the way I'm thinking about it. And it's led to this idea of bosonics. Okay, and you need to know, I wrote the abstract for this in 20 minutes, and it was one of those things I thought, oh, that sounded good. And then, okay, let's write a talk around that. So let's see what happened, okay? So I'm going to tell you about work that I've been interested in and doing for a large number of years. And one of the very enabling people is Professor Jimmy Hsu, whose group we've been collaborating with through that time. And then there have been many students, these are PhD students from physics, 5 of them, who worked on topics related to what will be bosonic insulators. And then recently, again, Jimmy Hsu here set up this collaboration with a group in China where we have evidence of bosonic metals. And there's a very primary person there, Chao Yang, and he came here and visited here, and I got to visit him a bit. So I'm really grateful for all these people working on this with me and leading to this stuff about bosonics. The National Science Foundation's been very kind, and Brown, as you know, Brown is you, Brown is really nice. All right, so again, this is going to come down to thinking about how much bosons want to be together compared to fermions. And we're used to thinking about bosons and fermions certainly in our first quantum mechanics courses. especially when we start thinking about multiple particles. And remember, condensed matter is lots and lots of particles. So one of the things that I found interesting as we did this work over the years was whether or not you could see statistical effects, particle statistical effects in condensed matter. How would it show up? And it's specifically in particle transport. So that's what we're going to talk about. So today, I will talk about fermions in condensed matter. And I am grateful for fermions, okay? So don't get me wrong. But bosons maybe have some neat things that we could maybe harness later. So we'll talk about fermions in condensed matter. And then I'm going to tell you something about potential bosonic states of matter. There seem to be limitations because bosons want to get together so much. They want to be in the same state so much that, in fact, there seem to be a limited number of states they can go in. So you have to kind of trick them to get them into new places. Then I'll talk about neutral superfluids, which were where we first saw bosons really acting well. Thank you, Caroline Onis. And then I'll move on to charged bosonic systems in 2 dimensions. And we're going to be working in 2 dimensions a lot. What that means for us is very thin systems, not too thick. And I'll tell you about superconductors. Then I'll tell you about the bosonic insulator that we were able to show existed. I got a late call at night from Stu, who was one of those PhD students, right in the middle of the night, 2 in the morning. I can't believe what I'm seeing. What are you seeing, Stu? You know, I had to get up and get out of the room, but it was really exciting. And then very recently, and we're revising a paper right now for Science about the possible discovery of a real bosonic metal. So let me remind you of what you may have had in quantum mechanics already. There's a range of students here. I am really grateful, especially for the first-year students who are in my class right now for coming. I know it's out of support. There are going to be things that you're going to see that you're not going to understand, but please just hang on, because you will see them again, right? So what we want to do is we want to put together particles, and some particles are fermions, and some are bosons. Let's focus on the fermions right now. They have half-integral spin. Now, when we put them together, so let's just do 2 particles. Let's not go to 10 to the 23 yet. You need to make a wave function for particles 1 and 2, and then go to state A or a state B. And when you do that, you actually have to make their wave function a sum of 2 terms. And in one term, particle 1 goes in state A, and in the other term, particle 1 goes in state B. And if they're fermions, you have to put a minus sign between the 2. That's how you write the wave functions down. And what that means in the end for fermions is if you swap 1 and 2, if I switch 1 and 2, psi, this psi goes to minus psi. It's negative. All right. The other thing that you'll notice is that if you make A equal to B, if they're in the same quantum state, psi goes to 0. They can't be in the same quantum state. They can't occupy the same quantum state. That's where the Pauli exclusion principle comes from. Electrons don't want to be together. You move them around, and they respond with a minus sign. Okay, but it's good. All right, so this is, I really find when I started talking to people about this, especially first-year students, when I was telling them what we were doing in the lab, why we were focusing on bosons and why they were so important, I found myself talking to them, about the periodic table of elements, because in fact most students hadn't really thought about what a fermion was until they got here and start taking quantum mechanics class. But everybody knows what a fermion is because you learned the Pauli exclusion principle in high school by learning the periodic table. So here's a periodic table. Chemistry is all about these electrons. If we go to copper, okay, what do? Copper is a big charged ball, and then it's positive, and then we start bringing electrons into it. We put 1 electron in, 1s, 2s, 1s, 1s, 2s, 2s. And so I can do this in front of students, and they immediately know, oh, yeah. They don't go in the same place. They don't go in the same state. And if that didn't happen, we'd have no chemistry. We wouldn't have a talk, all right? Which would have been fine with me, because I'm a little scared. Okay, so we wouldn't have chemistry. We also wouldn't have magnetism. And so this is something I got off the interweb. And so if you have 6 electrons, and so I guess this is carbon, Hund's rules tell us how to fill up the orbitals. So up, down, and then in fact, this next open orbital, you fill up one of these at a time, and then you go down, and then they tend to align. And again, this is due to the Pauli exclusion principle that they have to kind of go into different states. But there's also another thing that's going on, that in the process of going into this state and this state, you minimize some Coulomb energies, and you minimize spin-orbit coupling energies. So this is what fermions do. They have spin, they interact with one another through their spin and also through Coulomb interactions. And so what they do is they arrange themselves in this particular kind of way. That gives us magnetism. Thank you very much, because we have a net alignment of electrons. That's good. All right, so fermions are doing a lot of good stuff. And then I want to tell you one other thing. So this is now important. We make transport measurements. And so I'm going to be showing you transport measurements that tell us about bosonic insulators, things that don't transport current so good. And metals, things that transport currents well, but not like superconductors. So let me tell you how the Pauli principle operates in what a metal is. So the simplest picture of a metal, which works remarkably well, is to say I have a box provided by all those positive ions, and then I throw electrons into that box. Now the first electron is going to have a wave function with a wavelength which extends across the box. It'll have the smallest kinetic energy. Then I'll put the second one in. It'll have the opposite spin, smallest kinetic energy. Then I do this state, this state, this state, this state, for 10 to the 22. And if I look at K, which is 2 pi over the wavelength of the electrons, and I look at energy here are all those states. And so if I look at a piece of copper, I'll find that all the electrons are filling the lowest energy states and then up to a place called the Fermi energy. When the last electron goes in, it has a particular short wavelength and it has a particular energy, EF. Now, what I want you to notice in this picture is that the electron states are relatively close together here. If I want this to carry electricity, what do? Well, I put an electric field on it, and a picture that allows me to pretty much understand what the resistance is going to be, what the current's going to be, is something called the Drude A Model, or the Sommerfeld. What is it? Sommerfeld? I can't remember. Does anybody remember? Who's taught solid state recently? Come on, don't hang me out here. All right, okay. Well, I don't care anymore. All right, so electrons move like this. They hit something that they weren't expecting. They scatter. They hit, they scatter, they hit, they scatter, hit, they scatter. And there's going to be some average scattering time in the system. And during that time, the wave vector, the wave number is going to increase proportional to the electric field and that average scattering time. And so when you started with just a circle, this is in 2 dimensions, but it could be in 3 dimensions, a sphere of electrons, by putting on an electric field, you actually shift the sphere a little bit by an amount that depends on that scattering time and the electric field. And this works because the electrons can move here and scatter into another quantum state. In order for it to scatter into another quantum state, it's a fermion, that state had better be empty, or else it's not going to scatter into it. But there are lots of states, lots of opportunities, lots of options. So this is how we understand transport in a metal. It allows us to, well, understand the resistance as a function of temperature. So at high temperatures, it actually is a linear temperature dependence. That's why we have platinum resistance thermometers for telling your temperature at home when you have a fever. And then it goes down, and then it levels off to a value which we call rho defect, which is when you just have impurities that are doing the scattering. All of this scattering, by the way, is something that makes phase coherence very difficult. Remember, electrons are waves, right? They're waves. It's hard to see their wave-like properties because it's very hard for them to maintain coherence. That's going to be a big difference. Bosons love to go into the same state with the same phase and be phase coherent. That's going to be one of the big differences. All right, so I want to tell you about one other state of matter, two other states of matter that fermions can have. What you're looking at here is an insulator to superconductor transition. This is at very low temperatures. We're measuring the resistance as a function of temperature for a very thin film of bismuth. The resistance rises exponentially as you lower the temperature, going to infinity, we presume, at 0 temperature. That's an insulator. If you make the film thicker, it's remarkable, but at a resistance, which turns out that this is 6 kiloohms per square, which is H, Planck's constant, divided by 4 times the electron charge squared. It's the quantum of resistance for pairs. It turns into a superconductor. So these are superconductors. We'll talk more about superconductivity in a bit. I want to just say some things about the insulator very quickly. That in the insulator, the transport is different. Electrons are stuck in localized states. There's an electron here, electron there, electron there. I put an electric field on it like this, and they actually kind of hop and make quantum mechanical transitions through the system. It's not like they buzz around. And because of that, and because of their statistics, they actually show negative magnetoresistance. Their negative magnetoresistance is actually a fermionic quality. If I have a lot of time at the end, or you want to ask at the end, I'd be happy to talk about that, because that actually was responsible. One of the last times I gave a colloquium here was a while ago, and it was my talk before tenure, and I talked about that negative sign. Isn't that cool, Stefan? Yeah. Okay. So now I want to move on to potential bosonic states of matter. What's the difference between bosons and fermions? And I'm showing you a picture of a container filled with liquid helium at a temperature low enough that it's a superfluid. And if you look closely here, you'll see a little droplet, and here's an artist's conception of it, where the liquid goes over the side and it drips out. We'll talk about why that is. So bosons can form superfluids. They tend to condense into a single quantum state. They show long-range phase coherence. Today I'm going to tell you about how we can make insulators of them that are actually charged. And when we think about those insulators, we actually think about kind of superconducting or superfluid regions that get separated by non-superconducting regions or superfluid regions. There's local phase coherence, and then there's this metals question. The metals field is actually in the middle of kind of whoa. We're trying to figure out what's going on. It's kind of exciting. So let me tell you about helium-4. So helium-4 is a great boson. It's a great boson. It's helium. It's in the balloons. This is the pressure, temperature, phase diagram for helium. When you're up here at very high temperature, you only get a gas. You lower the temperature, you get condensation of the liquid at 4.2 Kelvin. You keep going down in the liquid, and there's this transition to superfluidity that occurs at atmospheric pressure at 2.172 Kelvin. At that point, superfluid helium shows you persistent currents. You start to wind it up in a circle, let it flow, it'll flow forever. It has infinite thermal conductance as well. And the way we understand those properties is to say, okay, there's a partial Bose condensation where a lot of the helium atoms enter what you might call a single quantum ground state. It's characterized by two parameters. It's characterized by the amplitude and the phase of the order parameter. The amplitude, well, let's talk about what that thing means. We'll do that here. Here's that superfluid order parameter. You square that amplitude, you get what we call the superfluid density, the amount of fluid that can flow without viscosity. If we want to understand how that current flows, what we have to know is how that current density, how that current density changes when we change the phase in space. So if you create a phase gradient in the order parameter, you actually get a supercurrent. That phase can fluctuate. that it can change in time. So imagine here are two places. One's in this fluid and one's up here. Oh, wow. So this has a chemical potential of mu1. This has a chemical potential of mu2. There's a driving force that actually tries to get this to move from here to here because of that difference, the chemical potential difference. Quantum mechanically, that means that the phase difference between those two places is going to evolve in time. And I'm not going to talk about this really. So I want you to pay attention to this. Phase differences that change in time and the superfluid current density. Currents, this turns into voltages when you have charges. Currents, voltages, those give you resistances. That's what you measure in an experiment when you measure resistances. Okay, so can you have superfluids in 2 dimensions? This was a big deal question for a while. Well, anyway. There was a theorem, something called the Merman-Wagner theorem, that said in 2 dimensions, XY models could not have could not give you long-range order, long-range phase order. You would always have fluctuations that would destroy order in 2 dimensions, the ordered state being the superfluid state. But experiments disagreed. So here's an example of one of the experiments. It was a very, in the early 70s, people were arguing about this quite a bit. What you're seeing here is, this is temperature, supercurrent magnitude. So people tried to get a supercurrent to go around a loop on some kind of a substrate. And this is supposed to be a thin film. And this group found that you could actually get a supercurrent to flow. Here's the magnitude. You lower the temperature, and you could get a big supercurrent. If you make the film thinner, you got a smaller one. Make it thinner still, a smaller one, a smaller and smaller. So you could get superfluid behavior in 2 dimensions. And then Mike Kostelitz, David Valles explained how that was possible. And Mike Kostelitz and Dave Valles got the Nobel Prize for doing that work. I don't want to say much more about it, except there is a phase transition to superfluidity in 2 dimensions. But please, just be silent for a moment. Nice. Okay. Hi, Mike. Some things, anyway, never mind. No, if anybody ever told me I was going to go to a place and like have neighbors who were Nobel Prize winners, I would have. So can we make a charged state of boson matter? And well, let's get started slowly. There's a state of matter called superconductivity, also familiar around here. This is mercury, resistance as a function of temperature. Communal onus, somebody in his lab measured the resistance, and then pow, the resistance went down to as low as they could possibly measure, as below anything they could measure. This was a superconducting transition. And the question was, at the time, was this Bose condensation? But there was this problem, electrons are fermions. What if they, oh, actually, they didn't even know about fermions then, did they? No, so they weren't even asking those questions. People asked them later. So what if they form pairs? So electrons have half-integral spin. What I didn't tell you about bosons is that they have integral spin. I put 2 electrons together, 1/2 + 1/2 equals 0, or 1, okay, which is integral. So this was explained later by Bardeen, Cooper, Schrieffer, Brown's Leon Cooper. And they found out that electrons were, in a metal, were unstable to forming pairs under the correct conditions. So an electron, this is a simple model of it, but an electron, as it whizzes through a solid where it has all these positive ions around it, and I mean whizzes through, those ions are like this, right? The ions move like this. An electron goes, whoof, an ion goes, whoa, right? What happens? The next electron that comes through sees positive charge and gets attracted to it before the ion goes back. Let's do that again. Whoa. And the other electron gets attracted to that. It's like it's getting attracted together. Those are Cooper pairing correlations. That's how you make Cooper pairs. Easy, right? Yeah. I don't know why it took them so long. Okay, yeah, all right. Well, there are lots of reasons, yeah. Okay, but they wrote down this amazing many-body wave function. It was the first many-body wave function that was written down that was non-trivial, that explained, you know, the behavior of 10 to the 22 particles. And it's so good that people are still trying to ruin it. And then somebody came through later and showed that you could have 2D superconductors. They did these experiments, and again, Berezinski-Kostelis-Thales superfluid transition. So that all works. So I will show you very thin superconducting films, and they superconduct, and I'm not upset about that. They should be. Thank you, Mike. All right, so now I want to tell you is electron pairs have real boson potential, right? Now, as Leon, I talked to Leon over the years about the work that we were doing, and there was on more than one occasion, I'm not a good listener, Leon had to tell me that Cooper pairs are not bosons, you know. And I'd nod like this, and then a week later I'd say something else to Leon, and you know, Cooper pairs are not, clearly I wasn't getting it. But, and that's true. The commutation relation for Bose operators that you need is not satisfied by the Cooper pair state, right? But there are situations in which you can get Cooper pairs to act like bosons. And you can do that if you're careful to let's see, confine the Cooper pairs to little islands and ask about the processes where a Cooper pair goes from here to here. When you do that, they are acting like a boson. They are intact. They are together. Yeah. So they have real, okay, so for the rest of the talk, I'm going to tell you about how we can make a bosonic insulator. I'll tell you about some of the properties, and then I'll tell you the evidence we have for a bosonic metal. Right? But again, we're going to be trying to make things that look like that. So again, the islands are there to keep the bosons apart. Because if you don't keep the bosons apart, they're going to condense into one state, which has phase coherence, and then you have a superfluid on your hands, and it has zero viscosity, and it goes through your fingers, right? Very fast. So what I want you to see, this is an image of what we think one of our films looks like in one of our experiments. Here are these little islands, and we're going to be thinking about transport. We're going to think about electron Cooper pairs going from island to island tunneling. There can be direct tunneling, and there can be virtual processes that actually affect that direct tunneling. That means we have multiple Feynman paths that get this Cooper pair from there to there. They're really kind of fun. So the islands keep the Cooper pairs apart. Now this is an equation, which is the Hamiltonian to get us to think about this. And let's see if I can get this through. So we want to keep the Cooper pairs apart. And this Hamiltonian tells us how well we're doing that. This term here is called the Josephson term. This is a negative energy. And what it says is that I want the phase on island I to be the same as the phase on island J. That way I'll lower the energy. When this EJ is large, it makes those two phases the same. It means the grains are really well coupled. This is a positive energy. It says this is the number of Cooper pairs on an island. As the number of Cooper pairs grow, I get a bigger and bigger positive energy. It's a charging energy. This energy tends to localize the Cooper pairs. This energy tends to delocalize them. There's a little bit of a competition. We make these little islands. If we get them really close together, this one wins, and we get superconductivity. If we pull the islands apart, this one wins. We get an insulator. Oh, wow. Okay, so really, I'm trying this for my first time. So I want to go back. Again, I want to say, here is the phase evolution for that Bose system. And for things that are charged, that chemical potential difference turns into a voltage difference, delta V. Here's the current. It goes like the gradient of the phase. If you have a superconductor, you have a supercurrent and no voltage difference. For an insulator, you have no current, but you have a voltage difference. For a metal, they're both non-zero. You have a current and a voltage. So this is the relationship between that order parameter, psi e to the I phi, and the things that we measure. This is the voltage difference, and this is the current. Does that make sense? I hope so. Okay, so let's do the Bose-insulator Cooper pairs, and I'll tell you about the system that we use to make it. So this is an experimental picture. What you see here is a refrigerator that gets down to temperatures of about 0.06 Kelvin, so it gets wicked cold. And then what we do is we put a little piece of glass, well, not a piece of glass, I'll show you. It's a piece of aluminum oxide. We put that here. And then what we do is we take pieces of metal, a green piece and a yellow piece. They're not those colors, but just you can see them. These are our evaporation sources. We run current through a heater that this little piece of metal is in. The metal heats up, melts, and starts to evaporate. It gets caught on the slide. In the same way water droplets get caught on the slide, get caught on them when you boil water in a pot. So we can make very thin films by heating up this metal, catching it on this slide, and then we get something that, because of a mask, we pattern it to look like this. So we get this bismuth film, and by doing successive evaporations, we can start thin and go thicker, 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 thicker in an experiment. And then we make, these are wires, we make resistance measurements. Now, we did something, we didn't know what we were doing at the time. We didn't know that this was going to happen, but now I'm going to tell you as though we did, okay? So no, I'm kind of lying in a strange way. So we used a substrate which had a surface that looked like this. This is an atomic force micrograph of the surface that we put here. The things I want you to notice is it has holes. And around the holes, I want you to imagine being in a little car. You drive up a hill, down a hill, up a hill, down a hill, up a hill, down in a circle. Now imagine that you evaporate metal onto this surface. All the metal that goes to the holes disappears. All the other metal coats those surfaces, and on those peaks, you get a thick film. In the valleys, you get a thick film. On the slope, you get a thin film. Because of cosine theta, you know, the whole cosine theta, the flux thing, right? The thicker films are superconducting. We can tune it this way, and the thinner ones are not. So we actually wind up with something that we're pretty sure looks like this, where the blue areas are superconducting areas, and the magenta areas are not. We've made dots. So as I said, in the experiment, we can go from thin films to thick films. We did that. We get a nice insulator. Resistance comes down as the film gets thicker. We see this kind of a dip up here. Maybe Cooper pairs are forming and trying to be a superconductor, and we make it a little thicker and we get a superconductor. This is a superconductor insulator transition in these bismuth thin films. Now what I'm doing here is I'm showing you again resistance versus temperature, but I'm going to take this scale and turn it over. So I have resistance versus 1 over temperature. Cold is over here. So zero temperature is over toward the wall here. This is called an Arrhenius plot. It's a plot that's good for measuring energy scales when you have an activated process. And what Stu found, who was the student that did this, his thin film, he measured the resistance as a function of temperature. It rose exponentially as he lowered the temperature. He made it thicker. The rate at which it rose exponentially dropped. And then it went through the superconductor to insulator transition. So, but what he found in this region was that the resistance grew exponentially as he lowered the temperature. And that's a sign that the carriers, the Cooper pairs, are actually stuck on grains, and they have to hop over a barrier to get around. Is this a bosonic insulator? Now, this was the fun, surprising part. Okay, oh, God, all these equations. All right, but they're good. They're good equations. So let's look at these. So I remind you that there were holes in that substrate. And now I'm going to remind you of something that depends. Maybe Gigi does this in mechanics. They see the momentum of a charged particle in a magnetic field. Does that happen, Gigi? No? Okay. So the momentum of a particle in a magnetic field, this is the magnetic vector potential, acquires a term which is proportional to the vector potential. And the vector potential is related to the magnetic field. What that means is a charged particle in this film gets a phase change due to the magnetic field. And it turns out that that phase change is periodic in magnetic field because of the holes. If I put on a magnetic field such that there's one flux quantum per hole in the system behaves as though, if this is true, behaves as though it has no flux quanta, or 2 flux quanta, or 3. There's a flux periodic behavior in the system if you have this change in momentum. There's something called the Aronoff-Bohm effect, and this is definitely what this effect is due to. So what we're expecting for charged particles in a system like this is that as we change the magnetic field, as we change the magnetic flux, we're going to see an oscillation in the momentum of the Cooper pairs. Oscillation in momentum is a change in the energy of the Cooper pairs. And so what we were looking for, let me go back a moment, is the following, is that, where did I put it? Oh, no. Yeah, never mind. So what Stu found was that he measured the resistance as a function of 1 over temperature, and it rose kind of exponentially here. He turned on a magnetic field corresponding to 1/2 of a flux quantum per unit cell, and it went high. He went to 1 flux quantum, it went back down. And the period is set by the charge, which sets the flux quantum. The period said that the carriers have Q equal to 2e. So the charged carriers were 2 electrons at a time. They're bosons. And then he did this experiment continuously, where he sat at one particular temperature and just changed the magnetic field and saw it go up, down, up, down, up, down, up, down, down. So he had a Bose insulator, what we called a Cooper pair insulator at the time. And I'm going to tell you one other thing. So we're talking about the phase. That phase dependence, this is a Bose system, is very strong. That's why we get these very strong oscillations. If you put on an even larger field, now I'm showing you resistance, temperature, and then magnetic field to much higher field values, here are those oscillations, and then you see a giant peak in the magnetoresistance. The resistance can rise orders of magnitude in a magnetic field. In a fermionic system, if you get a magnetoresistance which is 10%, that's a lot. Okay. And good. I'm going to skip that. So we saw a bosonic insulator. Now I'm going to tell you about the evidence for a Bose metal. And this is using a different system. And this is the system. Yttrium, barium, copper oxide films. Yttrium, barium, copper oxide. That's a high-temperature superconductor. Let me show you that here. So this is resistance versus temperature for films of yttrium, barium, copper oxide. As you can see, this one has a transition temperature which is, I guess, well, arguably, depends on where you measure it, it's above 75 Kelvin. Very high temperature. Those superconductors I was showing you before, the transition temperatures were like 2 Kelvin. There's a little bit of a difference. Now, what was done, and I believe this was Jimmy's idea, was to take these aluminum oxide substrates, pull off the oxide, which has this holy pattern, put it on top of the film, and then rain energetic ions onto the film. Those ions destroy the superconductor that it hits The parts that are masked, it doesn't destroy. And you wind up with a film which looks like little islands connected by little necks with holes in them. Very much like the films we were just looking at. And so you could drive it through a superconductor to insulator transition by using more and more damage. And if you look way down here, and now we're going to plot resist. I don't know where those came from. The resistance versus 1 over temperature. The resistance drops and then plateaus to a finite value. Less damage, it plateaus to a lower value. But the resistance becomes temperature independent at low temperatures. That's a real sign of a metal. I asked you to recall, I showed you the resistance as a function of temperature of a metal, and it went down and it flattened out before. Oh, that's kind of cool. Is this a Bose metal? Can we detect Cooper pairs? Well, we have those holes there. But let me first tell you that a lot of people have been working on this. Here's a paper that came from the late 90s on molybdenum germanium films. There is a recent paper on niobium diselenide films in a group that Leo Lee was working in, and they were seeing these metallic-like behaviors at low temperatures. We don't know what the mechanism is, but we think we've done an experiment that's going to help at least cut away some of the ideas. So now here are those metallic behaviors, and what we're plotting here is the resistance, the magnetoresistance, as a function of field for one of these at different temperatures. And what you can see again are oscillations. So there are Cooper pairs that are involved in this metallic state. It's as direct evidence as we can imagine. So like the Bose insulator, we see Cooper pairs by looking at these quantum oscillations. Now, these quantum oscillations, they occur, let's see, they occur because the magnetic field is affecting the phase of the bosonic wave function, right? So there's some coherence, but it's not long-range coherence. It's local coherence. If it were long-range, we'd have a superconductor. What was interesting to see is if you measured the oscillation amplitude of these films as a function of temperature for the metallic states, there is phase coherence that grows, but then it stops growing. So it seems like there's a saturation in the phase coherence in the system. We don't know what's causing it. We would like to know. So we saw a bosonic metal phase where we saw Cooper pair oscillations. And the metal has really low resistances, lower than we're normally used to. Yeah, we have to do more work. So here's the end of the talk. Good timing, Jimbo. Thank you. Bosonics. So what I'd like you to take away, is that bosonic transport involves phase coherence effects more than fermion electron transport. For the Bose insulator, we have Cooper pair tunneling transitions between islands, and the anomalous metal state has Cooper pair charge carriers, suggesting it's a Bose metal state, suggesting it's one where the phase coherence is somehow or another saturated at low temperatures, but we're not sure why. Thank you for your attention.
I will let you choose.
Oh, okay. Questions? Yes, Sean.
So, the superconducting arrays, just function arrays, in the old days, every time when you plot a curve like this, you would automatically, during that time,
You're talking about this one?
yes.
Yeah.
And then people would say, oh, this is the equivalent to quantum tunneling of vortices.
Yes.
Using that language.
Right.
But that language has been abandoned by the guys, I assume.
No. No. So what Sean asked is for this kind of a picture, people over the years have said, well, maybe this means that vortices, and vortices are what Mike worked on quite a bit. Vortices are windings of phase. That's 2 pi. If you move a vortex through a system, you cause the phase to change in time. If those vortices move really well, very easily, you can maybe get a metallic state because you'll always have a voltage, right? And if it's quantum mechanical tunneling, you can't get rid of it. You go to low temperatures and it keeps happening. And so I think there are still models out there that are suggesting that it could be quantum mechanical tunneling of vortices.
I remember Dan Shahar was strongly against that plan, and he changed his mind.
Oh, Danny changes his mind like the wind. No, Dan Shahar. That was one recent thing that Dan argued about there. Yeah, he thinks people have to be very careful with noise. Aside from that, we did the best we could getting with shielding and things. Yeah, is that good? Yeah.
So I might be missing or mixing concept. It's an unconventional superconductor, right?
The high TC is unconventional. Yes.
So have you looked at the point where you go from superconductivity to this Bose or transfer? Because there's in principle, we don't know what's the mechanism for high TC superconductivity. And then you're going into a state where you have Cooper pairs. Have you looked at that transition there? Where you go from that thickness, this intermediate thickness between seeing that this metallic state and seeing superconductivity?
So right down there, kind of in the weeds.
Yeah.
That's a very hard place to go because at some level, your ability to see this state is limited by how low you can measure how low a resistance you can measure. It's an interesting question, though. So is there something fundamentally that changes?
What about in the overdope side? When you go to this non-Fermi transport, when you get this linear resistivity?
Wow.
Can you see something there?
So these films these were optimally doped films. I don't know if the group is trying to make underdoped films or not. That you want to do overdoped where it's a really good superconductor.
No, plus when you get this regime where you have linear resistivity with temperature.
Right.
The square of the temperature is linear. So that's
Yeah. No. So actually, the cleanest films here, the ones that are least damaged, show that linear resistivity.
But you can see that in regimes even at low temperatures when you go to the overdose side.
Oh, if you put on a big magnetic field or something, it continues down. Is that what you're saying?
Even with this higher dome.
Okay. I'll have to look at that some more.
That could be interesting.
Yeah. Yeah.
That crossover too.
Oh, thank you. Yes, Stefan. Yeah.
So the late Jerry Groundler told me that when people started thinking about the Higgs mechanism, and he was one of the original people, they were actually thinking about the BCS model. They were thinking about generalizing that, right? And also Robert Brown told me the same thing. So they were, right. So this is so the naive idea that we've always had about the Higgs field, which is a boson, right, as somehow an analog of a superconductor, was that the superconducting state was bosonic. Now you've actually corrected this and said actually it's only when you confine these islands, right, it becomes bosonic or it has bosonic properties. So my question is, what is it about the confining that basically allows the sort of commutation relation to now look bosonic?
To look bosonic. Okay. So let me go back to this being on. And this slide I skipped. That's this slide. And so this has phase in it, and this has number. And these are quantum mechanical operators. And there's a commutation relation. And so because they have this commutation relation, in fact, there's an uncertainty principle. If I localize charge, I get big phase fluctuations. If I localize phase, I have no idea what the number is. Okay. And so if you're in a situation where n is the relevant operator. That is, you're changing the number of Cooper pairs on a grain. So it's some process like that, and you're measuring the phases. Then the Cooper pairs act like bosons. But you have to be changing. You're in I think it's Fock space. Yeah, yeah. So that's where you start to see it. Now, having said that, there are people who have tried to push superconductors into the Bose-Einstein condensation regime. They've tried to make materials where it starts to look more like Bose condensation. And there's some candidates out there where they think they're getting there for real without having to do this with islands. Yeah, yeah. Yes?
What happens if you make measurements with microwaves instead of DC resistance measurements?
So in the Bose metal phase, I'd be really kind of interested in any old phase. Yeah. So it would be really interesting to see. Well, first, I think it'd be interesting to see. So, no, that's like every time. When you put the microwaves in, you're going to start to see the energy gap between the ground state and the excited states in the system. And we think in the Bose insulator that there's going to be a finite window before you can actually absorb the microwaves.
So you don't want to investigate it in case you're wrong.
Indeed, indeed. No, it's as they say in New England, wicked had. Because these are so cold that the amount of, and they're so thin that the amount of microwave power that you use would always warm them up out of the interesting regime. But there are people trying. Yeah. Yes, Brad.
I think helium-4 could form a Bose metal state if you had appropriately designed disordered substance capacity.
So that's a great question. I was wondering about that. So I can only tell you my own intuition and my own prejudices on this, and it actually comes back to the question about YBCO being a different kind of a superconductor. I feel like you need long-range interactions. You need strong interactions between the particles to give you kind of the Bose insulator to give the repulsion. And then as you go toward the Bose metal, I'm wondering if you start tuning those interactions down. So there's something I didn't tell you. Can I tell you? Let me tell you. Bosons aren't the only story. So Shui Zhang, who just graduated recently, did experiments where he showed this remarkable thing about these Cooper pairs. When these Cooper pairs tunnel in the bismuth, when they tunnel from one place to another, some Cooper pairs in the vicinity break apart into virtual quasi-particles to screen that process, and then they go back. So there's some quasi-particle degrees of freedom, even as you just have the bosons. The quasi-particles are fermions. It's not such a pure story. There's nothing that's going to rip apart a helium-4 atom in a superfluid, unfortunately. Now, does that answer make some sense to you so far? Okay, yeah. So back to the D-wave superconductivity. We don't see the metal state in the bismuth films. We don't see that metal state. But you see it in the high TCs. And I'm wondering if those quasi-particle excitations, because it's D-wave, they go down to low energies, might be causing some kind of a process, which is Cooper pairs plus those quasi-particles. But that's just a wild guess. Yeah. Yeah, so. Oh.
Any chance of probing fractional charges?
If we could make them, I think, with the magnetic field, if we could make them and they had enough phase coherence, that'd be cool. But, so some of that in some quantum Hall systems, I think there were some experiments I heard about where they could see, fractional flux quanta, if you will, oscillations. Yeah. Yes, Jimmy.
You want to speculate on the consequences of having such a
Okay, let me, all right. Wow. So, when you have this phase coherence, you can have interference. And if you can somehow or another figure out how to tailor the interference to use it to kind of steer beams of these bosons, maybe you could make some really fascinating electronic devices that would be relying on kind of that quantum phase steering. That's my best. Jimmy, I leave those imaginative things to you.
So I'm imagining an experiment of having higher temperature on one side and a lower temperature on the other side. What do you think will happen?
How high is the high temperature?
Well, within your bosonic metal range.
Looking kind of for a thermal effect or thermal currents in the Bose metal?
Well, I'm thinking of the statistics. So if it's bosons, it goes by the boson statistics. So now what will happen? They will have to go from high energy to low energy.
And how does it convert from fermions to bosons?
I'm not sure we should, that's another possibility. But even if they don't, let's say they stay in the boson statistics.
Can they actually carry entropy and transmit heat? So in superfluid helium-4, the superfluid particles have no entropy. They just get out of the way so that the heat can be conducted. I don't know. That's a very cool idea. But I don't know. Thank you, Jimmy. I'll think about that. Well, this has been a delight for me. Thanks.